Hi, Rami. Sabine speaking. Hi. Hello. Oh, wait.
just going to check we're good. Hello, everybody. Welcome back to those of you who have seen our earlier Alert Online sessions. As you know, on Monday, we had our first session on the security around Internet of Things. We had our second session on Tuesday, for those of you that were here, a very animated threat intelligence session where everybody was disagreeing with everyone else. And it made for some very entertaining panel discussions. And hopefully those of you that were here and also watching via YouTube, I thought that was really an excellent panel since, yeah, it was very, what's the word, exciting. And then today, I think we have really one of the most exciting panels of the week of Alert Online, which is really looking at quantum technologies and the future of quantum computing. What does that mean? What's its impact on security? And what does that future look like? For those of you that are watching online, please remember that you can put all of your questions and comments on Twitter via #AlertOnline. For those of you in the audience, we expect your participation with questions and comments to the speakers. By saying that, I also would like to remind you, for those of you here today, that you can get your CPE points if you remember to write down your name and register on that green table. We're good. We also have some materials for you to take home today, stickers and other cool stuff if you're up for it. So, by doing that, I'd like to welcome our first speaker to the stage. I'd like to welcome Harry Buhrman. He's a professor of algorithms, complexity theory, and quantum computing at the University of Amsterdam. And he's group leader of the Quantum Computing Group and the Center of Mathematics and Informatics, CWI, and is the executive director of something very exciting called QuSoft, which is a research center for quantum software, which he co-founded in 2015. Harry, would you like to take the stage, please?
Great. Thanks. So it's great to be here and to talk about my favorite topic, quantum computing and quantum software. So let's fast forward 50 years in the future. And you went online and you went to Amazon and you finally bought a quantum computer. And one day it arrives and it's a rather big black box that stands in your doorway. And there it is. And now, of course, a big question is, what on earth are you going to do with it? And I guess I should say now, the answer, my friend, is blowing in the wind, because I just noticed that Bob Dylan won the Nobel Prize, but that has for literature, but that has absolutely nothing to do with this. So the question still begs, what are you going to do with this quantum computer when it's there? And you look up Wikipedia and you see that you have to do quantum programming and that it's counterintuitive and strange. And so I want to tell you a little bit on what you could potentially do with such a computer and what the obstacles are from a computer science perspective. And before I do that, I have to tell you first a little bit about quantum mechanics, which is a strange laws of physics that was discovered and developed in the beginning of last century by illustrious people like Albert Einstein and Schrödinger and Dirac and Feynman and Bohr. And one of the strange phenomenon of quantum mechanics is the notion of superposition, which says that an object can be in more than one state at the same time. A well-known example of this is due to Schrödinger, who had his cat be in two positions, namely dead and alive at the same time in a box. However strange this notion of superposition may appear, it actually has been verified experimentally many, many times, and as we speak it is being verified, and all the time the predictions of quantum mechanics turn out to be right. And so, first of all, with very small objects like photons and electrons, it holds true, but nowadays also with larger objects like molecules and viruses, you can observe this phenomenon of superposition. So superposition is something strange but real in our world. And basically this is what quantum mechanics says. So it is the most complete description of nature to date. It has the superposition principle, so a particle can be in two states at the same time. And then another funny notion that actually we know very well is the notion of interference, which says that the particle in superposition can interfere with itself. And you see here a picture of water waves that interfere, and that's exactly what can happen with these molecules and with these particles. And thirdly, there is a strange phenomenon called entanglement. If you have more than one qubit, you can entangle them, you can somehow link them in some way together, such that you get all kinds of effects that you cannot get classically with classical mechanics. This is called non-locality, and a famous example is the EPR paradox after Einstein, Podolsky, and Rosen. I will say a little bit about that later, but sort of these first two things, superposition and interference, are key to the rest of the talk. And so now the idea of quantum computing is to incorporate this quantum mechanics into our computation paradigm. And our computation paradigm is based on a single entity called a bit, which can be either 0 or 1. And actually, when you make it a quantum bit, it can be in a superposition of 0 and 1. And here in the middle, you see an artsy representation of a qubit. Of course, that's not what happens. What happens really is what you see on the right, which is a mathematical statement of what a qubit is. It has a little bit of 0 plus a little bit of 1. And how much 0 it is indicated by this number alpha, and how much 1 it is indicated by this number beta. And it has to be the case that if you square these numbers, I mean, they can be complex, and if you don't like complex, just think of real numbers. If you square them and you add them up, you have to get 1. So that's what a qubit is. And now, if you look at the qubit, something funny happens. When you do a measurement, you actually don't see the superposition, but you see actually 0 or a 1, and you see that with a certain probability. So with probability alpha squared, you see the 0, and with probability beta squared, you will see this 1. And actually, after you've done that measurement, you have destroyed the qubit. So it collapses, also something very strange. But that's what happens. So here's an example of a qubit, which is 1 over square root of 2, 0 plus 1 over square root of 2, 1. So what would happen if you were to measure this? Anyone has a guess? Grégoire, what would happen? He knows. 50%. Ah, very good. How do you know? Indeed, with probability half, you get the 0, and with probability half, you get a 1. And after the measurement, actually, this thing is broken. It is a 0 or a 1. And now this sounds like a little bit of science fiction, but it's not, because actually Grégoire works at a company where they make little machines that do that, at Quantique, and I actually bought one already, I think, maybe before you worked there even. I don't know. A little box, and it looks like this. You can plug it into your computer. I normally plug it into my computer, but now my computer is too far away, and when you plug it in, there is a green light coming on very reassuringly, and then you can generate random numbers that way. And so you get an interface that looks something like this, and then when you run it, you get a bunch of random numbers out. So these are old random numbers, and I could have prepared new ones, but nevertheless, this is also something tangible that exists and you can buy. And then, of course, Grégoire has to fight this question of, are they really random, these numbers? But that's a whole different issue. So, summarizing a little bit, it is a fundamentally different concept, this quantum computer. It's using these qubits, which are a superposition of 0 and 1. Each qubit doubles the parameters that we have. So with 300 qubits, you have 2 to the power 300 possible states in superposition at the same time, which is more than we have molecules in our universe. So it really goes through the roof. And the thought, sort of the leap of thought is that on these superpositions, you can do computations. So in principle, you can do a massive amount of parallel computing. So for the price of one computation, you can do 2 to the 300, which is fantastic. So all our problems seem to be solved. However, there's one problem, and that is, how on earth are we going to get the answer out of this computation? Because when you look at it, when you measure, poof, the whole thing collapses, like in the example with the single qubit. But when you have more qubits, the whole thing collapses to one single computation, and we're back to square one, where we just have a single computation. So that is not very useful. And so the way out is this second ingredient that I told you about, this interference. And this is what a quantum programmer has to do. He has to make use of interference to somehow interfere the computations that you don't want to see away. I'll give a small example of that later on. And amplify the ones that you do want to see. But bear with me that this is a fundamentally new way of programming, right? It's completely different and counterintuitive than what you're used to. So it's not that this quantum computer is a magic wand that exponentially enhances every computation. It's not, right? It only works for certain problems. So that's my next point. It doesn't really work for everything, but there are a few examples where it actually does pay off to have a quantum computer. And we really need to understand more of what this power is and what you can do with it. And a lot is unknown. And hence, it's extremely exciting to work in this area at the moment. So let me run by a few of the examples. It's not an exclusive list, but it's some of the examples that are very important, that I like a lot. And also some of the examples are problems that I worked on myself. So it is a little bit of a colored list, but nevertheless, I want to go through it. And I think the most important one is factoring large numbers, which is the first algorithm, sort of not the first, but the most important algorithm, I might say, that was developed by Peter Shor in '94, which allows you to factor large numbers in polynomial time, right? So 87 is 3 times 29. And to find these factors is a difficult computational problem, especially when these numbers get larger. We don't have fast classical algorithms to do this. They run, as we say in computer science lingo, in exponential time. So whenever you make your number a little bit larger, your computation time doubles. However, not on a quantum computer, as Peter Shor showed, because there is an efficient polynomial time, as we say that, but let's say this efficient algorithm that factors large numbers. And here you see the graph of, on the one hand, the classical thing, say on a 300-digit number, a classical computation would take more than 100 years. Actually, it would take thousands of years. This is a very moderate estimate. But on a quantum computer, on a modest clock cycle, would do this in a minute. So on a quantum computer, with this algorithm, you can quickly factor. And this is extremely important, and I think that's the reason why we are all here. That's because a lot of our security on modern-day cryptography is based on the fact that we do not know how to efficiently factor large numbers, like RSA schemes, electric commerce on the internet, all these, well, KPN knows very well. A lot of these cryptographic protocols, they are only safe if you cannot factor efficiently. When you can factor efficiently, all these protocols can be broken. And actually, so when a quantum computer exists, it can break a lot of these systems. So that's why it got a lot of attention, because it has this huge impact on our society if one materializes one day. Okay, so that is probably the most important one. Then, when you have a quantum computer that breaks cryptography, you also want to give something back, and that's the field of quantum cryptography, or cryptography in a quantum world. And now, actually, we can do something amazing. We can send qubits back and forth, right? And before we were hung up on just sending classical bits back and forth, but now Alice and Bob, who are sort of major players in the field of cryptography, they can send qubits. And there actually is a scheme due to Bennett and Brassard already from '84, so actually predating the quantum algorithm by 10 years offshore, where you can use it to generate a secret key between Alice and Bob. So a key of bits that only Alice and Bob know what the contents are. And once you have a situation like that, you can use that key to do completely safe encryption, completely unbreakable. And the idea of the scheme is that if you had an eavesdropper who would listen in on the conversation, then if he wanted to get some information about the qubits that are being funneled back and forth, actually they're only funneled forth, but nevertheless, if you had an eavesdropper who wanted to get some information out, this eavesdropper would have to destroy these states. Like I told you before, if you look at the qubit, you disturb it. Well, an eavesdropper has to disturb these qubits, And the protocol is so nifty that Alice and Bob can figure out that actually something has been disturbed and can retry until they have a key for which they are sure that nobody listened in. And so once you have that key, you can do any secure communication that you like. And again, Grégoire has a company where they sell this machine. And this is, I guess I should update the picture because this is an old picture. They have a newer version, but they have a version at least. You owe me, by the way. So actually, this quantum key distribution has also been done over large distances in the air. Here you see an experiment in La Palma, where I would also love to do my research, where they send it from one island to the other. They generated a secret key. And another thing that this quantum cryptography gives you is something that I've been working on, position-based cryptography. And let me illustrate this by the moon landing in '69. And actually there is a staggering, I think 29% of the Americans who say this never happened. This thing was actually staged somewhere in Hollywood. And nobody ever set foot on the moon. And so this begs the question, how can you prove that you are at a certain location? It's actually somehow useful. This position verification allows you to, for example, know that the launch missile command really came from within the Pentagon. Or you're actually talking to South Korea, not North Korea, which can be useful to know. Or it can prevent swatting. It's also the pizza delivery problem. And have you heard about swatting? No. So actually this is something real. And it happened to TV stars where people play pranks on them and they claim to be in the house of a famous TV personality and then say, I'm dying and I need help. And then sort of the SWAT team goes to this house. And then, of course, there was nobody there because it was a phone call from outside of the house. And so if that person who was playing this prank would have to identify him as being inside the property, it would be a lot more difficult to play this swatting trick. So anyhow, position verification is something that you cannot do classically, but you can do it quantumly under certain very reasonable assumptions. And actually on the same technology that uses this key distribution, you can build position-based crypto systems. We're so actually talking to the people in Geneva to do some implementations. And then last but certainly not least, I want to mention with respect to quantum crypto that it's actually more urgent than you think. We had this discussion already also at the table. And a lot of the times you hear this saying, well, quantum computers will take at least 10 to 15 years, maybe even longer, before they materialize and they will be able to break our current code. So we'll start worrying when these machines are there. We'll cross the bridge then. But actually, there's a big but, and that people sometimes forget, that is all encrypted information, especially when it's important now, can be stored somewhere by someone. So when you send something on the internet and it's secure, then that certainly is true, and it cannot be read, but it can be stored and still not be read. But now, once this quantum computer is there, you can actually read all the material that was stored, right? So if you want your message that you send now to be secure 20 years in the future, you have to do something now, right? If you want your message to be future secure, you need to use cryptography that is quantum proof, or it's also called post-quantum crypto. And you have to change already something now. So it's much more urgent than you think. So not urgent when you send your credit card information to Amazon, because in 20 years you will have a different credit card number. But when it's sort of a confidential message from one embassy to another, probably you want to think twice before you use old-fashioned crypto. So a third point is there are actually quite a few algorithms that can do things a little bit faster than classical computers can. So the Shor's algorithm can probably factor exponentially faster, but there are more modest gains to be gotten from a quantum computer, and those I titled under quantum search, quantum walk. And I actually want to zoom in a little bit on the quantum walk paradigm, because it somehow is nice and it shows you a little bit gives you a little bit of the flavor of what's going on. So, and also bear in mind that a lot of algorithms can be cast as a walk on a network, on a graph, where you want to find a marked item. But let's sort of go first to the most simple graph that we have, and that's a line. And let's start in the middle of that line at point 0. And now we flip a coin, and with probability half, you move to the right, and with probability half, you move to the left. So with probability half, you go to 1, and with probability half, you go to -1. And this you repeat. So again, if you were in 1, you go with probability half to 2, or with probability half to 0. And when you were in -1, you go with probability half to -2, or with probability half to 0, right? You see the picture, right? You flip your coin, and if it's 1, you go to the right, and if it's 0, you go to the left. And you repeat this many times. And when you do that, you get a picture that looks something like this. And I'm plotting here the probability over the time. So you can see that when the time goes on, sort of the probability that you move away from the 0 is a little bit, right? You're still very much concentrated on 0, as you can see. But you have you have a little bit of a variation, so you are a little bit away from 0 to the left or to the right. Right? So this is the probability, and the height of this little mountain tells you how much probability you have to be at a certain location. And so now let's do the same walk, but let's do it quantumly. So instead of actually flipping your coin and looking and going to the left or to the right, you actually use this box, but actually you don't measure it, but you use something that is happening inside there. And in superposition, you go to the left and to the right. So you split yourself. I mean, that's a little bit difficult to think of. And I see some of you think, God forbid, there's 2 of these guys. But anyhow, so you split yourself in 2, and sort of with amplitude now, 1 over square root of 2, you go to the left and you go to the right. And you keep doing this. And actually, there's going to be interference happening. And I'm plotting now what comes out. And remember the nice mountain we had in the classical case. This is what happens when you do this quantumly. It actually looks rather strange. It has these really weird peaks and valleys. And what you see is that the probability that you're now in the middle is actually much smaller. And you move to the left and to the right quite fast. Right? So after 250 steps, I don't know why it stopped at 248, but anyhow, at 250 steps, you sort of concentrated more on the outside, and in the middle there's much less. And actually this can be explained by the paths, sort of, you can think of this in superposition, there's all these paths going left and right, all happening at the same time, and the ones that go to the middle interfere with each other, and they interfere destructively, so the probability that you're there is very small, and the paths that go to the end, they actually didn't have a chance of interfering very much, and so you actually end up there. So you move completely differently, and here you see the two figures on the left. You see the classical walk, and on the right you see the quantum one, and it's rather different. And what is really different is that after t steps, you have a reasonable probability of being on t steps away, whereas in the classical case you only square root of t steps away. So this is a difference, a quadratic difference. And actually a lot of algorithms can be cast, actually all algorithms basically, can be cast as a quantum walk algorithm. And so you can use this particular difference to your advantage to do computation. And there's quite a few algorithms like searching on game trees, triangle finding, element distinctness, when you have a list of elements, figure out whether two the same or not. These are all very practical computer science problems. Matrix multiplication, that's something that a lot of people want to do. You can speed it up. And there's actually quite a lot of applications that you can do with these quantum walks that you can do more efficiently with such a quantum walk on a quantum computer. And actually there's also artificial problems where you even have an exponential speed up, like Shor's algorithm. Okay. So then a fourth bullet that is quite important and seems to require not so many qubits, that's simulation of nature. And actually the speakers after me will say also a little bit about that. But if you have a quantum computer, then you can actually simulate a quantum mechanical system very well. And this is actually something that a lot of people try to do nowadays. And I've been told that most of our computing time goes into simulating nature, and we cannot do it very well classically, because nature has this exponential blow up. Like I told you, right, with this 300 qubits, you have this 2 to the 300 many possibilities. Precisely this blow up is what prevents us from simulating nature very well. However, on a quantum computer, that is not a problem. And so when we have a quantum computer, you can somehow program it to do an experiment for you, and you don't have to go to the lab. And, well, the judge is still out what you can do then, but we anticipate that you can design new molecules, you can devise new materials like superconductivity, room temperature superconductivity, and there's even proposals to speed up the fertilization process. So this is very interesting, but we do need a quantum computer for that. And this may be very well one of the first examples where quantum computers show superiority over classical computations. Then finally, when you have all these computations and cryptography, there's actually another thing that comes to mind, and that is communication. Well, we're here with KPN, so they all know about communication here. And so early on, we wondered whether qubits can actually speed up computation. And actually, there's a theorem that says it can't. There's already a theorem from the 70s by Holevo that says if you have a message that uses k bits, then you cannot compress these k bits into fewer qubits. So qubits cannot carry more information in terms of bits than bits can. So it seems like communication is out of the window, but it's not, as we showed. For example, we showed that this problem of appointment scheduling, where Alice and Bob try to make an appointment with each other. And classically, you know how that goes, right? Alice says, hey, Bob, shall we meet on Monday? And then Bob says, no, Monday. No, Monday I have to go to the dentist. What about Tuesday? And then Alice says, no, Tuesday. I'm not available. I have to go to a lecture. And so on and so forth. It takes a lot of communication back and forth. And in our lingo, if your agendas are n bits, it requires n bits of communication. However, using qubits, you can do with only square root of n bits. And actually, this field has taken off since we started showing these examples in '98. And there's like many, many nice connections between other fields as well, between physics and computer science and math and physics. And so this is actually something that I'm very excited about that is starting to materialize now. I'll say in a minute, because KPN actually is working together with QTech on making a little network. KPN is giving their fiber, making it available for QTech to build a network. And here the network is envisaged between Amsterdam, Leiden, The Hague, and Delft. And so in Amsterdam there's QuSoft. And so I hope to run, and actually we've been talking to the people in Delft as well, to run some of these ideas that have been laying around for a long time on this network. And this will allow for quantum entanglement and for quantum distributed computing, but also for quantum crypto to be run here in the Netherlands. So that's very nice. Actually, communication doesn't have to go through fiber, it can go through air, and it can even go to the space station. So here's an example of states. You see on the left-hand side this donut that is running around. Those are states that can be sent up to the space station and be sent down. And these states that they can make, they are actually very suitable for a scheme that we developed in the early 2000s called quantum fingerprints, where it allows you to compare states much more efficiently than you can do classically. And so there are also ideas of actually sending our states, our fingerprints, up to the space station and back. So it's kind of neat. Okay, so there's a handful of the known applications, and I've listed them here again. And you can see sort of three themes. The red one is the computation theme. The blue one is the crypto theme, and the green one is the communication theme. And all these three are prominently present in our research field these days. So I want to, I'm good on time, so I want to end with a few of the things that I think are very important to address now, and sort of the immediate future, and a few of the things that I think, from my point of view, are important in a few years. So the immediate challenge is that we have less than 100 qubits. Actually, we have, I sort of figure out 22. It's sort of but it sort of depends a little bit how you count, and these guys will tell you exactly how to count. But we will have certainly less than 100 qubits, and I think it's a very important question, what are we going to do with these few qubits? So now we have between 10 and 50, and so it will only be proof of principle ideas that we're going to show with them. But once we get into the range of 50 to 100, there is the potential of doing something that we could not ever dream of doing before on a normal computer. However, what that exactly is, nobody knows, so this is exciting. Small networks that are being planned and are being implemented are, I think, very exciting. Actually, also see in Switzerland, there's a network. In China, there's such a network. So these networks, these truly quantum networks are being built, and we need software for them, and we need to know what to do with them. So there's a hardware question of building them, but there's an equal important software question of what on earth are we going to run on them. A third bullet is actually verification of quantum systems. If you have a quantum computer, it solves this task for you that you could never check on your normal computer or by pen and paper. Basically, that's why you had this quantum computer, because it does something that you couldn't do before. But how can you check that the answer is right? All right, so it tells you that the answer is 42 to your question. How on earth do you check that this is indeed the right answer? And so there are some nice ideas. Up to 20 qubits, you can do this brute force, but when you have more, it starts to be cumbersome, and when you have 100, it's impossible, and new ideas are needed. And there are new ideas around. And last, when you have so few qubits, you cannot afford to do error correction. And so maybe you can do some weak form of error correction, or maybe you can work around the fact that your qubits are not very stable. There will be dirty qubits that somehow are a little bit unstable. They're not completely a mess, but they're also not perfect. So sort of we live in the regime in between, and the question is, what can you do from a software point of view there? And then, of course, we have to program small devices, which is, for example, what they do in Delft, but what also Rami Barends, who is talking next, is doing at Google. There's a lot of software needed there to interface with the quantum hardware. So in the near future, so say maybe 5 to 10 years away, we will have more than 100 qubits. And then we can actually do error correction, but there's a lot of work that needs to be done to get that to work. We can do these quantum simulations that I talked about, so we can simulate nature. So that's cool, but also a lot of work needs to be done there. This quantum distributed computing is something that we could think of better, because now there's not only the network, the quantum network, but there will be little quantum computers on the end of these nodes, and that makes other possibilities possible. These search-related, these quantum walk algorithms can be used. One thing that people think of is, my time's up, but I need 1 or 2 more minutes, is quantum learning, which is a very hot topic these days. Classical learning, the question is, can a quantum computer help here? Or can a quantum computer help optimize at least some of the steps that classical learning is facing? And then, of course, there will be new quantum algorithms that I have no idea what they are now. And actually, somehow a philosophical, interesting question is a quantum theorem prover. Imagine that you had a quantum computer that can prove that a certain theorem or statement is true, but it really requires this exponential search space and interference to do so, and you can never actually do it yourself anymore. So a quantum computer will be able to, perhaps, I don't know, but potentially be able to prove statements that we cannot prove now, not even on a very big supercomputer. So I think that's also mind-boggling and very interesting. I indeed started a year ago a research center, QuSoft, in Amsterdam, that deals with these software questions, and sort of have the slogan now, enabling the power of quantum computers. And I think this is a fascinating topic. This is a joint venture between CWR, University of Amsterdam, and the Free University. Now going to a little bit to implementations. And I'm happy to give the stage quickly to my next speaker, but it's also a lot of progress has been in building qubits. Many groups worldwide are trying to build them. Next we will hear Rami Barends from Google, who has sort of the world record in solid-state qubits. Trapped ions, which is another way of doing building qubits. You see here an old picture with only 8 on the right, but in Innsbruck they have many more now, and in the States also. We will hear more about that later. D-Wave claims to have 2,000 qubits. Hopefully in the discussion we can talk a little bit about that. And actually we really need stable qubits, so the D-Wave qubits seem to be not very stable. We need stable qubits because if we have them stable enough, then we can actually do something that's called fault-tolerant computation, and we can keep them stable by doing computation on them. So it's kind of counterintuitive, but very beautiful. And I have a wish list also, what we need. And that's better hardware. So guys, build better qubits. We need better software, error correction, optimization, basically the things I've been talking about this 30 minutes. And then last but not least, we actually have to train new people. Oh, that's not how you write. Oh, not train, but anyhow. No problem. We have to educate new people, and especially because they are on the interface between computer science, mathematics, and physics. And you really have to know of these 3 areas to make some headway in this field. And sort of young people need to learn this and need to get very comfortable with this awkward model called quantum mechanics and this awkward computer called the quantum computer. And I think we should also invest in that. Thank you.
Thank you so much, Harry. I'm actually going to allow like 1 or 2 questions, because I'm assuming there's probably a lot more. We're going to save those for the panel. But if you have 1 or 2 questions that you'd like to ask now, and remember, we always say at Alert Online, the only stupid questions are the ones that don't get asked. So this is your moment to ask, can we predict the stock market with a quantum computer? It's time for those kind of questions, okay? So go ahead and ask them. Yeah, back there. Can we get a microphone to you first?
Well, what does a qubit look like physically?
Well, here's one.
Oh, that's a black box. I don't know.
Exactly. And when you buy a big one, I told you in the beginning, you get a big black box. But I guess that question, the people talking after me will tell you how qubits look like. So the physical implementation.
Yeah. Okay, we're going to have to wait for you to get a mic.
Yes, I was wondering, a lot of your software program algorithms are based on qubits, which are 2-state. Would it also be useful if you have a 3-state or 4-state qubits? Would that make making algorithms easier, or would it just complicate things?
Yeah, that's an excellent question. And actually the qubits may not be 2-level systems, but maybe 3 or 4-level systems. And in theory, that doesn't make a difference. The fact that you have 2-level systems or 3-level systems doesn't give you it gives you a little bit of a speed up, but not a tremendous speed up. So, and you can always somehow remap your qubit vision into a 4-level system if you wanted. So from a conceptual point of view, there's no difference there. Of course, when you have to implement it, it makes a difference. You have to program differently. But it doesn't mean that you can do much more, although you can do maybe a little bit more with the same amount of qubits.
Thank you so much, Harry. Thank you very much for that presentation. We're going to now go to the next speaker.
Yeah.
And the next speaker is going to be joining us virtually. His name is Rami Barends. And we already said Rami works at the moment for Google. But don't let that fool you, because he actually studied and got his degree in applied physics at the TU Delft, where he studied cum laude. And he specializes in experimental quantum physics with superconducting qubits, focusing on quantum logic, algorithms, and coherence, as well as fundamental processes in superconductors at low temperatures. Rami, did I get that right?
Yeah, thank you very much. And well, thank you for inviting me to join in this panel discussion.
Thanks, Rami. You can take it from here.
All right, I'll do that. Thank you. So my name is Ryan Barends. I'm part of the quantum AI team in Santa Barbara, and I would like to tell you about Google's efforts in quantum computing. The quantum AI team consists of a team of theorists in Los Angeles and a team of hardware engineers in Santa Barbara. And you can see here some pictures of the group at the beach in Venice Beach, some pictures of our lab. And I'm part of the team in Santa Barbara where we're tasked with developing quantum hardware. Now, we've all maybe heard of the story of the wise Indian sage who played a game of chess against the king and won. And the king was so impressed that he wanted to reward the sage and asked, what would you like in return? Whereupon the sage answered, well, I would like a single grain of rice on the first square, 2 grains of rice on the second square, and just go on. And the king thought, well, that's easy. Let's bring in the rice and start counting. And halfway through, the king realized he needed more rice than was available on the planet. And that's because 2 to the power 64 is quite a large number. It really shows the power of the exponent. And in fact, estimates of the total cloud storage space are in that range. Now, these storage space data centers are quite big. It's full of electronics, hard drives, and wiring. And that's because you have to store states classically in a bit. And essentially, a bit is a miniature switch. The state is either 0 or 1. In quantum mechanics, however, a state is a combination of both 0 and 1. And it's maybe easiest to visualize that as a sphere of which the poles are 0 and 1. And the state is then indicated by a vector pointing at a point on that sphere. And the vector has phases theta and phi, as you can see in the image on the right. And those are continuous variables that are controlled, in our case, by voltage and current pulses. Now, what's important here is that even the slightest amount of noise, external interference, parasitic interaction can easily kick that state vector. So quantum states are by nature very fragile. Now, for a single quantum bit, the computational basis is a 0 and 1 with associated phases. With 2 qubits, you have now 4 computational states, 0, 0, 0, 1, 1, 0, and 1, 1. And with just 64 quantum bits, you end up having more states than the cloud. And this is really one of the hallmarks of quantum mechanics, that you're able to have this exponential state space. Another hallmark of quantum mechanics is quantum tunneling. And it comes in very handy when we want to solve minimization problems or optimization problems. For example, we'd like to find the global minimum in the left image. The potential landscape is on the right. Now, suppose we start in A. Now, A is a local minimum, and it's not so easy to pull yourself out of that minimum and find a lower minimum B. But quantum mechanics allows for the state instead of jumping over the barrier, to tunnel through and find the well in B, cool down a bit more, and tunnel through again to point C. Now, given enough time, it may tunnel through D, but it works best when barriers are tall and narrow. And interestingly, that's the case for problems of a higher complexity, of a higher polynomial order. Now, combined with the exponential state space and quantum tunneling, you can really start to see how quantum mechanics becomes a natural resource for computation. And it's a potentially vast resource. Imagine how we could put in all kinds of different material configurations or molecule configurations and try to find an optimum. So it is a vast natural resource for computation, which we have not been able to tap into as mankind. And at Google, we're trying to change that. An important part of quantum mechanics is quantum measurement. Harry already touched on this subject. I'm going to read you this great Dilbert strip. How's your quantum computer prototype coming along? Great. The project exists in a simultaneous state of being both totally successful and not even started. Can I observe it? Well, that's a tricky question. And it's indeed a tricky question because measurement will return a classical answer from all that state space. All that exponential state space is collapsed into a single classical answer. So a good algorithm uses that quantum state space and then gives you an answer. And examples are, what is the optimal configuration of a molecule? Where is the minimum in a certain optimization function? And that's really well suited for example, minimizing a binary function, which is used for machine learning in classifiers, such as those used for image recognition and language translation. Now, I have to say that this is an emerging field. People are searching hard to find ways where this can be really implemented. Another application is materials research. To give you an example, superconductivity is a physical phenomenon where the resistance vanishes below a certain temperature. Now, most materials have low critical temperatures, as it's called. There are some materials which have relatively high temperatures, but there the physical mechanism behind superconductivity is not fully understood. Imagine if we could try out different material configurations in our quantum computer and try to see which one superconducts best, shedding light on this physical mechanism, and perhaps use a quantum computer to create a designer material which would superconduct at room temperature. We could replace the materials used in power lines, where 8 to 15% of the electricity is lost in power lines and transformers. It would decrease our carbon footprint. Another example is use in chemistry. I'm going to talk about nitrogen fixation. It's a process used in the manufacturing of fertilizer. Mankind uses the Haber-Bosch process to capture nitrogen in ammonia, as you can see here. It is a process which occurs at high temperatures, high pressures. It's a bit dangerous. Sometimes fertilizer plants explode. It's an energy-intensive process. It consumes 2% of the world's energy. That's coal, oil, anything. And last year, sales of nitrogenous fertilizer, and there's also other fertilizer, is 68 billion. So it's a big field. Now, the Haber-Bosch process is one of the important reasons why we're able to balloon to a world population of 7 billion without an increase in arable land. So it's a very important process. Nature, on the other hand, uses an enzyme, nitrogenase. It fixates nitrogen at ambient temperatures, ambient pressures. And at its center is an iron sulfide core. Now, iron disulfide is an element which, if you want to perform a full simulation, we can't do that. So we can look at it, we can be in awe of it, but we can't replicate it for ourselves. All right. Let's try to build some quantum hardware. Nature is intrinsically quantum mechanical, so we could go ahead and take a hydrogen atom and use its lowest energy levels as a computational basis. Instead, we chose to work with superconducting quantum circuits. Effectively, it's an LC resonator whose lowest energy levels now are used as computational basis. And using such a quantum circuit has advantages. For one, you need to be able to control your hydrogen atom, and putting a wire on an atom is pretty hard, actually. It's rather easier for us to simply place a wire next to the quantum circuit, and you can see that the cross is being connected to by several wires. Another reason is that this kind of technology is compatible with nanofabrication. So you could, in principle, walk to a foundry and get a large-scale system out. And number three, the cross is kind of the center of this quantum bit, and you see a lot of a light area that's metal around it. So it's intrinsically in its own Faraday cage. And that's very important because the key challenge in qubits is to balance connectivity, coherence, and controllability in a manner that is scalable. As said before, the cross is the cross-shaped structure is the capacitor. The inductance is then formed by the little square loop at the bottom. That's a square superconducting loop that is intersected with very thin aluminum oxide barriers. And there's a supercurrent sloshing around in that little ring. And by applying control currents or magnetic fields, we can tweak that supercurrent. And that allows us to make this qubit frequency tunable. And we'll be using that to turn on and turn off interaction in our system. At Google, we actually have two development routes. One is digital quantum circuits, and one is analog quantum annealing. Now, these are different routes, but there's a lot of overlap. We need to develop similar materials. We need to think about coherence. We need to develop electronics to control the whole thing. We have to implement or figure out how to wire it up from all the way from room temperature down to very low temperatures. So there's a lot of overlap here. This is an example of our 5-qubit digital quantum device. You can see the 5 qubits on a row. It's in red, 5 on the line. Readout is on the left. Those squiggly lines are readout resonators. And on the right, you can see all the control wiring coming in to control these 5 qubits. And we'll be using the frequency tunability of the qubits to enable interaction. If quantum bits have a different frequency, they hardly talk to each other. So interaction is effectively turned off. But by bringing them closer together, the natural interaction in the system is that the frequency starts to get pulled. So you can see in the middle picture, you can see that the state factor of the orange qubit in this case starts to rotate around the vertical axis depending on whether the other qubit is in a 0 or a 1 state. When we're done with the interaction, we can pull them apart again, and now we have an entangled state between these two qubits. This is called a controlled phase gate. And in fact, there are many gates. I think maybe you know from classical computing, there are Boolean operations. You've got your NOT gates, your controlled NOT gates, AND gates, OR gates, NAND gates. Some are reversible, some are not reversible. Quantum operations all have to be reversible. And they're all defined in terms of rotations around these different axes of this sphere. So there is a NOT gate, and that's simply a rotation around the x-axis. There's also, you can make it a controlled NOT gate. There are also Z gates. Those are rotations around the vertical axes, and you can make that also controlled, as I showed you before. Let's put this in use in a simple example algorithm. Suppose qubit A is in a superposition state, and I'm going to visually represent that by a blue arrow and a red arrow at the same time. And qubit B is initialized in the 0 state. It's in its ground state. Now, what we could do is we could rotate qubit B onto the equator, then perform a controlled phase gate. And remember, with the controlled phase gate, the state will rotate around the Z vector, depending on whether qubit A is 0 and 1. And that's indicated by the addition of a red vector in the searchlight of qubit B. And finally, we'll rotate qubit B back onto the Z-axis. And now we see we have an entangled state. The state is 0, 0 plus 1, 1. And that means that when we measure qubit A, qubit B is also the same. Whether it's qubit A is 0, qubit B is 0, qubit A is 1, qubit B is 1. Whether qubit A is in the Netherlands, in Santa Barbara, or on the moon. And that really is quantum entanglement. Okay, let's take a chip and cool it down. We use a superconducting system operating at frequencies of 5, 6 gigahertz. And we need to cool it down to very low temperatures, to 20 millikelvin. That's 0.02 Kelvin above absolute zero. And that's done in a dilution refrigerator. And I'm always impressed with these systems because it's kind of a meter and a half tall. And at the top, the temperature is room temperature. And it cools all the way to 20 millikelvin. And somewhere in between, you actually go below the ambient temperature of the universe, which is 2.7 Kelvin. Now, these switches here have a lot of wiring. There's a lot of magnetic field shielding, infrared shielding. Several experiments can be run in simultaneous fashion. So this is really our workhorse here. And let's take our system and try to run a simple algorithm. Well, I already showed you a little example algorithm before how to create an entangled state between qubit A and qubit B. Let's implement that here. And you can see that right here. So on the bottom, you can see the algorithm, and on top, you can see the, I'm going to show you the density matrix. And what you see here is a 4x4 matrix showing you the populations and correlations in that quantum state space. Now you can clearly see 4 red bars. 2 red bars with arrows, the diagonal elements, are on the 0, 0 and 1, 1 element. And that means that the state is 0, 0 plus 1, 1. And the off-diagonal elements tell you the correlation. So that is a positive correlation. So it's a 0, 0 plus 1, 1. You could also have 0, 0 minus 1, 1. In this case, it's plus. Now, the nice thing about this algorithm is that it's scalable. So we use 2 qubits, but we can pull in a third. And you see now that the state space is 8 by 8. And we still have 4 bars, indicating we have a state of 0, 0, 0 plus 1, 1, 1 with a positive correlation. We can put in the 4th and even put in the 5th qubit. And what's interesting about this experiment is you really see that the quantum state or the quantum state space increases exponentially, but you'll still see those 4 clear red bars. And so that shows that we still have quite good control over what goes in the state space. And that's always a challenge, but it worked out well for us. And this was working out so well that we decided, well, let's build a 9-qubit version of the system. So here you can see 9 crosses on a row. I think it's okay. 9 crosses on a row with the readout resonators at the top and the control wire at the bottom. And we're going to use this system to start simulating a little physics. Let's look into spin problems. And a spin problem is related to minimizing binary functions. And we'll relabel our qubits as a spin. And in a spin problem, you have local fields and couplings. Now, suppose there are, and that's indicated by, so the local fields is indicated by the yellow arrows, and the couplings are indicated by the red and blue cylinders between those little balls. Now, if there were no couplings, the solution is trivial. The spin would align with the local field in the same way an electron would align to a magnetic field. But when you add couplings to the mixture, it becomes, it no longer is a trivial matter. For example, if 2 adjacent qubits have an opposite local field but a positive coupling, it is no longer clear what's going to happen. It's not just a classical thing. And you can see such a configuration at the right end of this chain. Let's start with a simple example problem. We have a starting configuration where there is no coupling and there is a same direction of the local fields for all qubits. The solution to this problem is very simple. All the qubits will align, or all the spins will align with these local fields in the same way a weather vane would point into the wind. Now, we'll slowly decrease the local fields and slowly ramp up the coupling strength to create a problem configuration where we have equal couplings but no local fields. In essence, we're asking the quantum system to find a solution to the following question. What is the state in a chain with equal couplings? All right, let's run this. Let's initialize the system. All the spins are pointed, are at the equator, aligned with their local fields. And let's start running the sequence. So we'll slowly ramp down the local fields and slowly ramp up the coupling strength. And we'll do that by taking that interaction, chopping it up in a single qubit and 2 qubit gates. So we really construct the interaction and to run that. So it's a digital simulation, as it were. And you can start to see after step 1 and step 2 in the density matrix that the element, the populations and the coherences in that state space start to slosh around, but it's not yet clear what happens. We're halfway only. And after step 3, 4, and finally 5, you can really see that the middle starts to become emptied out, and you see 4 bars on the corners grow. So the system found the final state of 0, 0, 0, 0 plus 1, 1, 1, 1. And that means that the spins are aligned either way. And yes, that's the answer to our question, what state would you have in a ferromagnetic chain? Well, the spins are aligned either way. Now, the fidelity of this process is 55%, and that is due to the accumulation of gate error and effects of noise which occur during this whole algorithm. Now, we even ran a larger random problem, and that's a problem I showed you before, where we have local fields, where we have different coupling strengths and signs. That's on the left, the problem configuration. On the right, you see the outcome. In dark gray is the ideal outcome, and in red, the red bars are the experimental results. And you can see that the majority of the red bars are on the left. And that means there's still a significant amount of correlation in the system. If there would be no correlation, it would be all random, you'd get a uniform distribution, and this is clearly not that. Now, we really pushed our system. This is kind of as far as you can go with what we have here. But this is a pretty large simulation in terms of qubits and gates. I believe it's the largest digital simulation in the solid state. In fact, what we did is we took a digital quantum system, simulated an analog quantum computer, and let that solve a problem. And now these and other demonstrations have really made the field excited, or they have really have made people excited about our field and started a technology development. We're vested in superconducting technologies. Other people are using photonic systems, ion traps, cold atoms, and V-centers, semiconducting qubits, and even Majorana fermions. But in all those platforms, it's important to realize that you have to have the whole chain working. Now, in our case, we have a quantum integrated circuit. You can see 9 qubits on a row, but there's still a lot of wiring and readout going on that chip. And we have to connect to that. So if you want to do that at a larger scale, you have to connect to all that wiring via carrier wafers. It's also all these qubits have also need to be read out simultaneously, ideally. So you need a wideband, high-power, quantum-limited amplifier, and that's something you have to develop yourself. That's not something you can buy, and that all needs to work at low temperatures. I mean, temperatures used are 20 millikelvin, and you can see the amount of filtering and wiring going on in there. Now, all the wiring goes up to room temperature, and there it has to connect to a control hardware. And this control hardware needs to be able to accurately control many qubits simultaneously with low noise. So this is something which is kind of specialty hardware, and you have to develop that yourself. And finally, that whole thing needs to be controlled with software. So here's an example of the assembly-like language you use. Place a qubit in a certain state, move it to somewhere else, let it interact here, measure. But all that needs to be compiled. The waveforms need to be generated. They need to be corrected for the distortion in the cables. That needs to be separated out and sequenced, sent to the control boards, and then run. And this whole chain needs to be able to work to run your quantum computer. I think we and other labs in academia and industry have started to made beautiful demonstration experiments. And with these larger systems of 5 and 9 qubits, we can start to see a little bit where we want to go. And we want to decrease the amount of gate error, especially the error in the 2-qubit gate. That's a tough challenge, but it's a great one. And we have to increase the number of qubits. And when we're able to do so, between 10 and 100 qubits, we can start to think about implementing error corrections. The errors of the system are low enough that you can start to correct them. They become robustic and small nodes, if you like. We can start to also run quantum supremacy algorithms. When we increase the number of qubits and keep the error low, we can start to implement logical gates and finally logical qubits. And at higher numbers, you come at or arrive at a fully fledged quantum computer. Now, with all these demonstration experiments, you can say we have kind of learned to fly. We kind of touch upon this physics. We have made convincing physics demonstrations, but the goal is to reach the moon. And that requires a lot of technology development, a lot of understanding the physics in these materials and in these systems that go on in low temperatures, a lot of algorithm development, software development, all needs to work. And it's a beautiful challenge. And one could argue that it is perhaps one of the largest computational challenge for mankind in the 21st century, right? Build me a quantum computer. The physics works, but we have to learn how to use it. Thank you.
Thank you, Rami. I'm going to just ask, are there 1 or 2 questions we can take now? Oh, yes, go ahead. Let me just get you a microphone.
Yes, thank you. So Google announced it would achieve quantum supremacy by 2021. That computer, would that be also capable of distributed quantum computing?
Your sound is a little low, but you asked about quantum supremacy. So I'm not going to give time ranges for that. I think it's clear that we have to decrease the gate error and increase the number of qubits, and that's hard. It's also a challenge, but we have to do that. Now, one of the things we can do with 40, 50 qubits is something called quantum supremacy. And what you would do in that proposal is basically run random circuits and see whether there's a coherent outcome. And at 40 to 50 qubits, you have a quantum state space which is really beyond what even major supercomputers can do.
Yes, but in the case of what you will develop, is it possible to hook them up to each other and use 2 smaller ones to make one bigger quantum computer?
Well, that's a good question. So the challenge there is to have a high fidelity connection between the quantum bits. And so far, what has worked best is to place them next to each other without any kind of wiring and just have them feel each other through capacitive coupling. And that's something that can be done easy. It's reliable, it's robust, and it's reproducible. And if you start to play with wires and cables and connectors, it is a pretty tricky business. So I know we have to scale up what I showed you.
Are there any other questions? I was just wondering, Rami, while you're here, I'm just conscious that maybe not everyone knows exactly what quantum supremacy entails. Could you perhaps give a short explanation of what that is? Because the guy who's been asking the questions twice has an unfair advantage over the rest of the audience.
Sure, yes. Well, quantum supremacy is achieved when a quantum system or a quantum computer can do something classical computing cannot. And the easiest, the most achievable low-hanging fruit there is to have a quantum computer run a set of random circuits with, I think, between 40 and 50 quantum bits and have a coherent output. And that's a pretty tough challenge because in that algorithm, there cannot be any error in the quantum computer. There cannot be any bit flip or phase flip or any single qubit or multi-qubit error. It needs to run in a pristine way. And that's a big challenge. And for that, the errors need to be lower than we have now. But if you are there, you can actually run in hypothetical algorithm in a way a classical computer cannot. The 2 to the power 40, 2 to the power 50 is just such a large number. It can't be reached with classical computers anytime soon.
Cool, thank you. With that, I'm actually, you're going to hang out for a little bit longer?
Yeah.
Yeah, okay. So with that, I'm actually going to take it over to the next speaker, Thomas Monz, who I'm going to invite to take the stage. He started his study in Innsbruck No, go ahead, please. In 2000, and in the 2002 summer breaks, he worked on ultra-cold atoms. I thought this was really impressive, actually, because now that we know what types of different qubits there are, his accomplishments are counted by the entanglement of up to 14 ion qubits, a world record that stands to this day. So it's a pretty illustrious set of speakers we have for you today. Fourier transformations in terms of outstanding achievements regarding your PhD and your postdoc, experimental quantum simulations of lattice gauge theories. There's just so much cool stuff you did. I'm having trouble telling all of it, so I'm not doing you justice at all, but perhaps it's just good to proceed with your talk.
Yep.
Thanks, Thomas.
So my main intention here is to give you a feeling similar to what has been asked before in the audience. What does a qubit look like? I want to give you a feeling that's similar to when we look in the audience and say, how many cell phones, which ones do we have? Someone says, I want to have an Apple product. The next one says, Samsung is a great thing, which you're currently not allowed to use on an airplane. There are different devices that you use, different approaches to technology. And so far, you've mainly heard about superconducting approaches. You've seen the challenges there. But there are also other approaches on getting a quantum computer done. And at that point, I can't really say which one is better, which one is the one who's going to win. But obviously, each of these approaches has advantages and disadvantages. And very likely, on the long run, if we support those parallel avenues, there will be something that we learn in System B, which we can then map over to System A. We bring 2 or 3 technologies together, and in the end, a fruitful evolution of those systems will very likely give us then a quantum computer that really fulfills our dreams. So when you look at an old, let's say, do you see that? Yeah, it actually works on the screen. So there was an old paper from The Economist which highlighted back then 3 main runners on quantum computing. What you see in blue, that's the superconducting system. That's like Rami was explaining us about. In the center, photons. Photons historically, when we look at our colleagues here, photons were the first experiments where like EPR and so on, where people started to think about quantum and so on. So obviously, when everything you relate to quantum, to EPR, is photon-based, some of the ideas are, can I use a photon for computation? And then, luckily for us, because that's been the main workhorse of myself, there is also calcium. It's like trapped ions on that slide. But actually, the list is way, way longer. So we also have Rydberg atoms, for instance, from Mark Sefferman or Antoine Brouvet. So like Sefferman would be in the US, Brouvet would be in Paris. There are impurity-based systems which you have locally with, for instance, Ron Hansen. Also quantum dot systems. There is also D-Wave, which is slightly different technology. And so what I want to show you now is this system in some simple terms. What do they look like? How do they work? Just a rough idea. That's all I can provide in a given time. What you see in the top left, it's an ion trap. It's just, I would say, roughly the size of a fist. The old designs are the size of a fist. You use 4 blades. They create an RF field, and because the ions are charged, what that does, it actually stores ions in the center. And in this system, it's quite easy to add ions. That's something which is an advantage in some sense from the atom community. I can just add 1 more ion. I don't have to change anything on the hardware. I just let this oven where the calcium is evaporating, I just keep it running a little longer, and I can go easily from 1, 2, 3, 4 ions to 20, 30, 50, which we did. While working with currently, it's about 20 ion qubits that people are using these days. Prominent representatives would be, for instance, Rainer Platt in Innsbruck, Chris Monroe, Dave Wineland at NIST. It gives you a rough idea. On the other hand, you would say, fist-sized something, how can it be that my quantum computer, this internal chip, it's larger than my cell phone? These can be made smaller. There are approaches, for instance, from Sandia, from GTRI, and so on. The newer chips which are developed, the footprint is I would say, roughly on the order of 1 millimeter by 1 millimeter. And it's wire bonded, so the very same technology, in some sense, that you've seen from Rami. It's the same which is mapped over with respect to how to trap ions. So these can be made smaller, and that has a big advantage there. If you want to store ions, if you want to keep a single atom somehow with your optical tweezer with an RF field, if you want to keep it there, you have to think currently what's around us, it's air. So the air molecules would constantly bump into their ions, and you can't have that. You don't want to have it. It would destroy your coherence. The ions might get lost. You have several problems. You have to build a vacuum chamber around your setup. But that vacuum chamber is roughly the size of a football. With these newer traps, we can actually make vacuum chambers when you, for instance, look at NBL, where the entire chip, including vacuum, including oven, and so on, it's smaller than the size of your palm. And this is like a chip that you can just put into a mount, and if it breaks for whatever reason, you just throw it away, you put the next one in. So it gets to a stage similar to other chip designs. Historically, the next system I want to briefly talk about would be photons. You'd think, well, photons, how would that look like? You could go into any quantum optics lab. What you see there is very likely a big table, lots of mirrors and wave plates and so on. You'd say, oh, a PhD student was standing there. He aligned everything for weeks to optimize the distances and so on. And once I want to run a new experiment, he has to start from scratch again. He would just throw everything away which has been on the table and start from scratch. And that's not what I'd like to do. And so people have been looking a lot into, can we map, actually, when you look here at the company, can we use telecom-like technology and use that for quantum computing? Is there something like a photonics chip where if I want to do, let's say, a superposition of left and right, can I directly program that into a waveguide array? And that's possible. So one of the most advanced chips that I know of are, for instance, from Anthony Lang in Bristol, but there are also advanced experiments from Can Wai Ban, from Andrew White, from Philip Walter. So location-wise, to give you a feeling, that would be UK, China, Australia, Austria. Then, coming more now to chips and even smaller systems, it would be, for instance, quantum dots. That's a tricky one. What we are dealing here with is, if you thought that atoms, like really working with a single atom is already challenging, these systems go even a step farther. What they work with is basically 1 or 2 electrons. They use a structure in such a way that they can really keep and store that single electron, and there is, again, you can define a 0 and a 1, and they can manipulate them, for instance, by applying currents on those wires. They can manipulate them and work with them. Given the technical challenges there, you see there is a certain drop in the number of qubits, whereas ions are confident with 10 to 20 ions. Photons work roughly close to 10 photons these days. Quantum dots are still experiencing and working with how do I hook up two electrons. So usually there's a certain trick behind it. What they usually do is they encode one bit of information in 2 electrons to make it more robust against noise. So if you talk about 2 qubits, actually would be talking more along the lines of 4 electrons. Superconducting, I'm just briefly mentioning here for completeness. What you see here is, for instance, the 5-qubit system from Jerry Chow and Jay Gambetta at IBM. It's again a small chip. One thing that I want to state there, which I personally find really amazing, is all the systems that you see here, well, maybe besides that one, in the morning a student gets up, it has to do some rough alignment of the system. He spends an hour or 2 loading ions, optimizing RF control, and so on. IBM, that's the current, this quantum computer on the cloud. From what I know, that system, that 5-qubit system has been automated to a point that they switched it on, I think around February or something like that. And from what I know, Jay nor Jerry nor John Smalley nor any one of them, they didn't touch that system now for close to half a year. And that means it's automated. And the remaining task at that point is now to go from 5 to 6 to 7 to more qubits. And that means, and that's the cool thing about it, this machine, it just runs and runs and runs. I haven't heard of a blue screen yet, but yeah, we'll see. Then another system, which is kind of atom-like, you will notice when you think about that. In that case, we've been talking about storing a single atom in vacuum. Over there, we said we generate a structure where we manage to store like a single electron. In a very same way, what you can also do is you can say, I have a crystal, for instance, for Ron Hansen and Tim Damignau, it would be, I take a little bit of a diamond. What I can do on purpose, I can let's say create a fault in the structure one way or the other, and then what I manage to do is this fault, in some sense, it still traps an electron. Let's say an electron is missing or electron can be there, depending on how you do it. And in that case, you can also store. Like it's like an artificial atom in some sense, but good thing is now it's not an atom where I have the challenge of keeping it in vacuum so that nothing interacts, but this is really now a diamond. So I can take the chip from Ron and I can move to Innsbruck and just install it, and I don't care. I can keep it in my pocket more or less. Whereas if I want to do the same thing with an ion, it wouldn't work. I would have to keep the vacuum all the time. The very moment I have one leak, I'm screwed. So there are certainly several advantages to such an approach. Besides, and that might be something interesting, besides diamond structures, for instance, Andrew Zurak and Morello in Australia, they are working on a similar approach which is based on silicon, where again foundries exist with existing technology where you can just use them. And they are currently on the 4-qubit level, so they've been able to implement, for instance, error correction. And one interesting candidate, for instance, with respect to scalability, it's Rydberg atoms. A Rydberg atom, it's just an atom. What you do is you on purpose excite it in such a way that the electron is so far away from the core that you can almost think about it, the electron is gone, but then the electron is swishing around your core. It's a little bit like a magnet. And then you can, similar to what you've seen from Rami, you can have those magnets interact with each other. While the interaction-wise, and that brings me to Harry's statement from the beginning, like how do you count qubits of a certain system? So you might notice, Thomas, why do you say they work with 2 qubits, but I see something like 8 by 8 atoms there? So the trick is currently they have the capabilities, the control to make 2 interact with each other, but at the same time, some of the structure of the experiment makes it really easy for them to create large registers. They are just lacking currently the control of working with those. And that, again, addresses one of the questions in the audience. So the strength of your cell phone, it's for the Netherlands, might be KPN in the background. What you do is, the cell phone on its own, the core, the computer in it, it's really weak. What you do is you use the internet connection to ask someone else to act on your behalf. So if you want to have a strong system, it would be interesting to have capabilities of interfacing it with another, let's say, stronger, larger quantum computer. If you want to do that, how would you do that? It actually is not so bad, and it's in some sense you again can borrow technology from telecom. What you want to do is you want to preserve this quantum coherence. If you heard in the beginning, there are quantum computers based on photons. So obviously, what I can do is I just have to map somehow from my stationary qubit to a photon qubit. For atoms, for instance, most of the systems approaches are based on just putting mirrors around. What means when you can use some special schemes where you excite it, the atom throws away a photon, and with the mirrors around, you can predefine where the photon goes. And that basically maps from the atom in the center onto the light field. The same applies with Rydberg. The same applies for the nitrogen vacancy centers, for instance, as Ron Hansen is working on. With photons, there's nothing to add. And for the superconducting systems, the only one that I know of, it's Oscar Painter at Caltech. There it's physically, it's a little bit more involved because the energy gap between your qubit, where like Rami said, it's roughly in the gigahertz scale. If you want to get 2 photons, you have to map suddenly to 10 to the 14 hertz. What you do there is you basically connect the current to a piezo, where a piezo is a device when you apply current to it or when you charge it, it creates a pressure or a force, and that in combination with, let's say, a grating, that then influences the light field. And so you can, with the detour around the piezo effects, you can start to get photons out of a superconducting system. So quantum computing at the end, that's going to be the final slide. What I want to convey at that point is we've been talking a lot about quantum computing, but similar to what Rami said, quantum computer, this is like getting to the moon. There are many interesting aspects before that. If you think about, for instance, the currently discussed, developed quantum technologies flagship, they define roughly four pillars. The first one would be communications. And there already exist companies that use quantum effects for communications. The next level in complexity would be, for instance, sensors. When you look at France, they, for instance, have muquants where they use quantum effects to have gravimeters. These gravimeters can be used, for instance, to detect iron ore. So you go along a street and you notice for some reason the gravitational field increases, so there has to be more mass below you. It could be iron. There are other interesting, that's why there's a gyroscope that I like a lot. There are, what you can do is you can have this sloshing atom cloud as a very sensitive system that tells you whether you moved or not. And that's, for instance, is used in submarines, where they can outperform previous system, I think by more than a factor of 100. In terms of switching everything off, you just float around in the water in the dark. And I think even after a day, they know within a meter where they are, without tracking, without any GPS. Simulations, that would be, for instance, something that D-Wave could be useful for. And at the end, if you go from left to right, at the very end, there will be then quantum computation. But there are interesting aspects that we can, let's say, commercialize and use already at an earlier stage, with some representatives also being in the audience. And that's already it.
Thank you. I'm just going to ask you to stay here for a moment. Do we have any questions directly for Thomas now? Okay, well, I actually have a question because I think you guys aren't daring to answer the questions because, you know, you don't want to seem silly when you don't understand necessarily what's happening there or what the guys are saying. Because how many of you actually know, Thomas mentioned what IBM is doing with their cloud platform. How many of you know what that is? All right, that's one guy who keeps asking me all the questions in the first place. I would really like it if you could explain what that was, because that's why he was talking about the 5 qubits and that system actually never needed a PhD student to fix it. Please first explain what that is. The level.
In some sense, you can simply say, yes, a very, very small-scale quantum computer exists. There are 5 qubits, you have full control, you can log into, like you log in, you get an account, you can upload certain experiments. For instance, Harry might have a really good idea and a new algorithm, and for some reason he only needs 5 qubits. Then he wouldn't have to bother and calling me and say, Thomas, do you have time? I have a nice idea, let's try to implement it with ions. He can just say, well, actually there is a quantum computer on the cloud. I have my own account, I know my pulse sequence, Jaya or someone is helping me in translating his idea into a sequence. You upload it to that system, you wait, from what I know, it's a few days, not much more than that. And you will actually get the results of your quantum computer back. So anyone who thinks the quantum computer is still 10 or 20, 50 years away, it's a question of how you define a quantum computer. If you think a quantum computer is something which is computationally compatible or like outperforms your laptop, yes, it's farther away. If you want to have access to a quantum device which shows a superposition which has aspects that can't be directly covered in your normal computer, with 5 qubits, you can create your account, you log in, you just let it run, you directly get the answer out. So yes, a very small-scale quantum computer exists, and to give you a feeling, the very same system has been used, for instance, for all those aspects like error correction and so on. So if you're interested, just get an account. Honestly, I don't know the email, like the web page now by heart. But if you probably dial in IBM Cloud Quantum, then you very likely one of the first 2 or 3 links is going to get you there. So yes, the quantum computer exists, and you are free to use it.
That's pretty cool. Actually, I find that mind-blowingly cool. And the fact that it actually has this system that doesn't require the massive amounts of setup every day is also amazing. So I would really like to encourage all of you, and also those of you watching, to ask these questions. And please don't let the speakers, get away with just keep going on if you don't know what they're saying. The point of these people being here is for you. So, yes. Wonderful. Love that. Great.
I've got a question. You talked about, I think you talked about interfacing between separate systems with superpositioned state, like having a photon move from one system to the other.
Yeah.
Would that integrate to quantum computations to one? Or is it just communication and preserving the secret, like we stated before, of the actual the message, for example?
So the way probably everyone has a different idea now what we do with the photons. No, but the way you can look at it is, let's say you have either a chip from IBM, a chip from Google, an iTrap from me. There will be 10, 20, 30, 50 qubits one way or the other. And I have a problem now which is larger than that. If Harry now says, I can give you actually an algorithm where you can separate, like you can parallelize some of the computation, and you only at times need to have those two sub-blocks talk to each other, then you can use this quantum interface to have one system do part of the computation and one part than the other. There are problems, and that might be interesting. It's basically why we built those supercomputers. There are problems where you want to minimize this talk between A and B as much as possible. And if you got the problem which you can't parallelize, then all of us are screwed, and so you have to build a larger and larger system. But that's also neat, because that means that the IBM people won't get around just building one 5-qubit system after the other and then just interconnecting them, but we have a good reason to push them to get to 10, 20, 50.
Okay, thank you.
I'm actually going to go ahead and start the panel now. Thomas, if you'd like to take a chair. I'd also like to introduce our two other panelists, which are Rogier Verberg, zeg ik? Yeah, who received his PhD in physics and is part of the awesome group at TU Delft, part of QTech, who is actually working on building a quantum computer.
Actually, yeah, we are really trying with multiple platforms, so we can discuss about the pros and the cons.
Please go ahead and I'd also like to welcome Grégoire Ribordy, who is from the was from the University of. That's where we met. I'm always confused. I'm like putting you back in the University of Geneva. He's actually one of the founders of QTech, and what did I say? QTech. Oh dear Lord, it's a faux pas of ID Quantique. And actually, how long do we know each other?
About 15 years, I would say.
God, that makes me feel so old. But I saw one of his first. I think I visited your lab at University of Geneva. Yep. So he's awesome, and he's one of the pioneers in this frontier. So welcome.
Thank you.
Yeah. I'm also going to ask. Actually, if we can get him back, Rami, and I'm also going to invite Harry back on the stage. So. I want to make it very clear, again, you guys have a Twitter hashtag, Alert Online, where you can submit questions and comments to the panel. I encourage all of you to take advantage of the people sitting here to also ask simple questions. What it's about, I'm just going to kick off one, just to make it very clear why we're here and why we're doing this. What is, because we saw in your presentation the amount of qubits you need, and we talked about, having 10 qubits to 50 qubits, etc. We talked about how to actually build those qubits. We had Rami explaining how you would actually have some functions running on those. So let's actually talk about what is the definition of a full-blown quantum computer. What is that exactly? What's viable?
That's an interesting question. Actually, I might... give it back to you. What's the definition of a full-blown classical computer?
Right, but I'm not on the panel. That's your job.
But that's something we all know,
right?
What it is. So I guess it's a bit. I guess if it does something for you that's useful, I would call it a quantum computer.
But what's full blown? I mean, what's viable? We talked about the the IBM cloud-based 5-qubit. Is that enough to actually do Shor's algorithm?
Well, actually, you have a nice paper on Shor's algorithm. It needs slightly more than 5 qubits, but not much more. Like, how many do you have?
Well, in that case, it becomes tricky with counting.
Yeah.
So to give you a rough idea on why it's not so simple to count qubits or bits in that sense. Assume I give you an algorithm where it's fully sufficient to give you the like not the full-blown answer in one step. Let's say you want to know your bank account number and you want to read it off, and it says for some reason there are, let's say, 1,321 euros on your bank account. You could say 1,321, but I can also say, well, it's fully sufficient if you give you one letter at a time. So I can say it's 1, and then it's 3, and then it's 2, and then it's a 1 again. So there are algorithms where you can, let's say, read out the information bit after bit, and in the meantime you can reuse that qubit in your algorithm. So let's say magically for some reason, the system in principle would provide you a 20-bit answer, but you only need, say, 3 plus 1, and this one system would be reused 10, 20 times. It's hard to answer how many qubits you'd have and what the complexity of the algorithm is there in that sense.
Yeah, but your question was, is it a full-blown quantum computer? And I think, well, first of all, quantum computers are not going to solve every problem more efficiently. So actually, for most of the problems, like maybe doing word processing or whatever you do on your computer, you won't need a quantum computer. So for those you don't need. So it's going to be a special purpose device, and we've shown some of the potential applications that could be used. That could be used for. So we're really not after a quantum computer that can do word.
No.
So it doesn't have to be a full-blown computer in that sense. So it will be a special purpose computer. And I would say the device of 5 qubits already is one.
Okay.
Although that is not doing something that you couldn't already do on your normal computer.
No, but assuming the algorithms that we're talking about now, which we presented in the presentation of, I think, your presentation or your presentation, where we're talking about Shor's algorithm and using that to do factoring at a large scale, we could pose a threat to current classical cryptographic systems. They're asymmetric. So from that principle, 5, no. 9?
No.
No, not 9.
Really? So,
I would say that I think I agree with Harry here. I think the thing is it useful? Mm-hmm. And it's like your classical computer. If you would have a cell phone which has 5 bits, it can't really do much. It's basically an electrical abacus, and you just look at it. It's nice. That's it. But that's not a full-blown quantum computer. No, I think it's when you're able to address relevant problems. And what we have to keep in mind is that in many cases that requires something called error correction. Mm-hmm. And that means that there is an overhead. So you need many physical qubits to form one logical or one like error corrected perfect one. And typically the overhead is around 1,000 to 10,000. So if you want to have maybe 100 logical quantum bits, you'll probably end up looking at a system with 1 million physical quantum bits. And right now we're at 9, so I wouldn't call that a quantum computer. I would call it a quantum device or a quantum circuit, but not a full-blown quantum.
So I suppose I'm going to get the answer back, like for the next question about, how do we see that evolution, Rami, in classical computers? But the question is around timeline. So when did the developments for a quantum computer start, and which stages, challenges, breakthroughs, have we done so far? Where do we see that, like we just talked about 9 versus 1 million, in terms of our evolutionary track here? So where are we now? And, we're speculating about will be 5 years, 10 years, 15 years. What are we speculating now when we think, okay, this is actually something that is worthwhile to solve a legitimate problem?
I think it is, at the moment, you talk about the quantum circuits we have now. We can control 1 or 2 qubits pretty well, but we don't fully understand all the relevant interactions. So if you come to a somewhat larger network of maybe tens of qubits, There are a few errors. Rami pointing out error correction. There are different types of error that require different strategies to deal with. And figure this all out for a larger number of qubits is still a lot of work to do.
Yeah.
So in that sense, we don't have the first full-blown quantum circuit yet. Maybe somewhere halfway. I mean, the development of the classical computer took about 40 years from a transistor to a, let's say, mainstream computer-like device. Well, I think the field is already working on quantum devices for maybe 15, 20 years for the first qubit, the first device. And the next 20 years or so, a lot of focus will be on scalability. If you want to have at least maybe 50 to 100 logical qubits, and you take the overhead, Rami is pointing out, maybe 1,000 to 10,000, so you end up with millions of physical qubits. It's a lot of scaling we have to do.
Yeah. Actually, the question is, I suppose, directed. Last year we had, I'm going to take your question just after this one. Last year we had a panel at Alert Online. Grégoire, you were there. And we had it with cryptographers. So we had cryptographers who are, let's put them in the classical category, which will not offend them, hopefully, too much. But and then we had people who were working on post-quantum cryptography. And the question was around, when is it needed? The questions around when will we have one is more around which response will be required, specifically from a cryptographic standpoint or a security standpoint. And I remember Phil Zimmerman saying there's going to be cold fusion before there's a quantum computer.
Well, we're saying, you know, this usual criticism is to say quantum computing is like fusion, cold fusion, because it's 20 years away and it's been so for the last 20 years. So, you know, is there real progress? And you know, that's maybe an interesting question: is can we see signs now that indicate that we're making progress toward a useful quantum computer, or are we still really at the very beginning where there's a question whether it's doable or not? And I guess these people here will be, you will have lots of example to show that there's actual progress going on, and I think so. That's why, you know, we had this discussion last year about crypto, and for me it's very frustrating because I'm more on the security side, and I always get this question from the cryptographers say, you know, quantum computing is so far away, and I think it's a very good idea to do a follow-up session this year to try maybe to give this kind of elements also to these people. And so in practice, maybe you guys have to answer because it's not my area of expertise to give time estimates.
I'm trying to put it in context of why we want to understand, you know, viability, timeline, development scales. It's really about having adequate responses ready. And you were talking about the race to quantum, and it's not just of, you know, which type of, will it be a Ferrari or will it be a, I can't think of another Formula One car. Sorry, I'm a girl. But if it's, you know, a Ferrari versus something else, but I think there's a country designation here that's relevant. Will it be the Chinese? Will it be the Americans? Will Europe need to work faster to keep their secret secret? I suppose that's really the question.
But actually,
I'm not sure that's, if I may.
Sure, go ahead.
Yeah, so maybe the discussion shouldn't be like in how many years is there a quantum computer which can do something. Maybe the discussion should be more that like we now know that the cryptography we use is sensitive. Theoretically, it's you know is sensitive to a quantum breaking. And maybe now we should already look into changing what we're using. And our quantum key distribution is one way to go. Another one, for example, is used post-quantum encryption. And in fact, actually, Google already rolled out an experiment. It's called a New Hope algorithm, where they use the lattice-based encryption, and that's something you could actually use on Chrome. And that's one of the ways to try out to be ready for that. So I think the time to start thinking about this is now, independent of a timeline.
Yeah.
If I may add something here, this is, of course, a very reasonable answer that Rami gave. The problem is that when you go into risk management, you have so many priorities or challenges that you need to deal with that you need to prioritize. And so if you want to ensure security, you know, you have a limited budget, many problems, what do you do first? And so you will put quantum safe somewhere on the list, depending on the answer or the estimate that you'll come up with in terms of when it will be relevant.
Exactly. What's the urgency?
Exactly.
Yeah.
And so I think you should keep asking to get a date from these guys because they need to give us a date.
Well, one number that I can throw there for like if you look at current programs, there are incentives to push error correction in the US, but even closer to us, look at the UK with their 2020 program where they want to have a network of 20 qubits, like 20 nodes in each with 20 qubits, and that by 2020. So maybe they don't do it by 2020, but by 21. But it gives you an idea if that network works and if that system works. There ought to be a scalable system which gives you very swiftly on the order of 100 qubits, and it's probably not too far away.
2020 is around the corner. So if we have 100 qubits by 2020, that's interesting.
Well, and it's not too far off because when I started with the ions, we did gates with we implemented Dirac Solar gate. It was a 2-qubit gate. That was around 2002, 2003. That was a big achievement when it was published in 2004. So that was 2 qubits. Already a few years later, it suddenly was 8 qubits, and everyone was like, "Yeah, we're never going to go beyond 8." 2 years later, we did the 14. Recently, we did topological encoding. Every time when a PhD student left the lab at 4 o'clock in the morning and said, "We're never going to do anything harder than that," 1 or 2 years later, we just surpassed that by a factor of 2 again. So. Yeah, well, you burn some PhD students on that.
Always good, always good. I'm going to take the question that's the audience.
I hear a lot about error correction, about qubits and physical implementation of qubits, and it just made me wonder whether how error correction is implemented. Is this a statistical thing with a lot of qubits, or is it like a checksum kind of solution?
It's really, I mean, you take, in very simple terms, what you do is you have, let's say, 3 copies of a bit of information, and so that would be the classical equivalent. And what you do is you use a special quantum compatible way of figuring out, are all of them the same? Or you do a majority vote, and then if out of 3, 1 of them had a certain error, you can still say, well, assuming that really only 1 error occurred, you can correct for that. And that's really done. So the ion trap community did it, the photons did it, superconducting did it. And NV centers, also so that would be, all of them did it. I think the only ones that is spin qubits and who was the other one, the 6th one?
Don't look at me, dude.
Photons.
Photon. Yeah, okay, but they lose anyway. Yeah. But basically, the currently stronger communities, all of them implemented error correction already.
But I mean, the question was, how does it look like, right?
Does it work?
And so you know about this. I mean, you were talking about checksum in classical error correction, and quantum error correction actually looks a lot like that, although it is more complicated because you don't have to only correct bit flips, but you also have to correct all kinds of other errors that can occur on your system. But basically, they're kind of checksums in superposition. That's sort of
that's a good way to put it. Yeah, no, that's a great way to put it.
Well, the key in error correction is to not just correct the memory, which we could do with majority voting, but protect quantum data while it's running an algorithm. And that means that you can't measure data qubits while it's going on. So majority voting is not compatible with that.
Well, what I said was...
How error correction works is that you basically test parity. And parity is something that allows you to look at changes without looking at the actual data. So in a error-corrected quantum computer, you basically have continuous error correction cycles, and on top of that framework, you implement a logical algorithm. But the basis is parity detection, at least the error correction we use.
So that's why I said quantum compatible. You can also look up a non-demolition measurement on figuring out whether they are the same without really knowing what they are. And that's how you can do the equivalent of a majority vote.
I see another question here. I also saw a hand up there. Where's the microphone? Oh, you've got it. All right, I suppose possession of the microphone counts for speed here.
Well, I thought about there was this other computing system like neural networks, and they have this million-core Spinnaker project somewhere in the UK. Is it possible to simulate qubits Like have a classical computer and just have it run 20 qubits simulated machines?
Well, yes, you can, and as a rule of thumb, the overhead you pay in simulating an additional qubit is a factor of 2. So if you have 20 qubits and you want to simulate it, it costs you 2 to the power 20 time steps, which is still reasonable. But as soon as you go to 50 or 100 or 64, as Rami had as an example, then this becomes not feasible anymore. So you can simulate small systems, small quantum systems, but you cannot simulate big ones.
There seems to be kind of an agreement that about 40 to 50 qubits, there's the threshold of what you can simulate with classical computers. Even the mainframes have their limits over at 40 to 50.
Okay. And we have another question here. So we have someone else with a microphone. Yep, you're shortest.
Okay, well, this is a bit of a follow-up on the previous item about error correction. Does this also correct for common phase shifts and common errors that are systematic over many qubits?
So depending on the setup, actually, if you say there is a common error, like a symmetric error, there are ways of encoding information in such a way that you use that symmetry to, for instance, make the entire system directly blind or insensitive to that kind of noise. So, for instance, one way of looking at that would be, it's called a decoherence-free subspace. Given that you have the symmetry in the noise, you can go into that subspace and do something there. It's again a factor of 2, basically. You would have to use 2 qubits to encode then one smaller. It's not a full-blown logical qubit, as some theorists might call it, but still you can encode it then in a factor of 2 more qubits. And then, for instance, noise like a magnetic field over the sample, if it's homogeneous, then would entirely drop out.
Know what it looks like.
Sorry, could you
that's the tricky part.
Then you already know what it looks like. Then you can correct for it.
But of course, if there's too many errors, then you cannot correct for it anymore.
Yeah, well, I was coming to that because I have a question in that area. All this is very amazing work, but there are also some critics who think that it will never be possible to achieve the accuracy in the coherence and the interference and the interactions. People like Gil Kalai, etc., that write papers on it, and they think you will never get enough accuracy to make large-scale quantum computation possible. What is the viewpoint of the panel on this?
Well, so actually, we were discussing this over lunch, but actually for accuracy, you don't need that much accuracy as long as you have 1 over polynomial, so 1 over the time that you run your computation accuracy, then you're fine. For example, if you would run Shor's algorithm to factor, then if the accuracy is like that, say 1 over, well, what's the running time, n squared or something, then you will get the factor with reasonably high probability. And then once you have that, you can rerun your algorithm several times to be absolutely sure that you get the right answer. And in case of Shor's algorithm, you can actually check by multiplying the factors you get to see that it is correct.
So that would mean that you need better hardware for larger numbers.
Yes, but not exponentially. You don't need exponential precision, which would be unrealistic. You need reasonable precision.
Okay, thank you.
I understand this criticism, but you have to bear in mind that it is a fairly young strategy to correct for errors. I mean, a few years back, people thought we could not correct for errors because if you do a measurement, you destroy your state. So we found out these disparity measurements to at least to do something about it. Now the new theories on error correction bring down the overhead, this from the number of physical qubits to the number of logical qubits, down from tens of thousands to thousands. And well, we are claiming that we built a computer hoping that also the theory people work on the smarter algorithms that make us require a smaller overhead. And there are some other strategies. Some qubits potentially have a much longer lifetime, better stability, to require far less error correction in the end. So I think it's not a steady state, this field. I mean, we have new theories every year still, and it still has to be figured out what is the best strategy, if there is a single best strategy at all.
Yeah. Feel free to jump in.
But of course, it could be that the errors are so bad that we cannot fight them. but we don't know. We simply just don't know whether that's the case. And so that's not a reason to say, well, it could be potentially very bad, so let's not start, right? I mean, we're starting, and we first have to figure out whether that's the case.
Yeah, we certainly need to try, of course. But I was just wondering your viewpoint.
There's a good hopes that it's actually not at all as bad as Jill Kalai is saying.
One more aspect that would be if you believe, if you believe in the theories when they say there's the theorem, beat that threshold. I mean, both John Martinis, the IBM people, the ions, all of them are, depending on which theorem you follow, but the gate fidelities, like the error rates, go down by a factor of 10 roughly every year, at least in recent years now. Error rates are at 10 to minus 4, 10 to minus 5 level and still improving. So I think Oxford team with David Lucas, they are at close to 10 to minus 6 level now, which would be below those thresholds. At least this single unit. Once you then, again, we come to the scaling problem, just because you have it on 2 qubits, once you have a third and a fourth, does the error still, the model behave the same way? That's an engineering problem. But in principle, the raw numbers that you would assume for a certain model from the theories, we are already there.
So
yeah, so for example, the error correction, we are using.
Go ahead, Rami. Sorry, we have.
Oh, sorry. Yeah, it is a little. So the error correction we are using, for example, has a pretty clear threshold numbers, and the single and 2 qubit gate operations we use to implement the error correction need to have a fidelity of like 99.8, 99.9%, which means it's allowed to screw up once every 1,000 times. And that is something we are a factor 3, 4 away from. So that's not; those are not crazy numbers. So those seem reachable with good hard work.
I'm going to take the next question.
Yes, on another level. Sorry, I have 2 questions. The first question is: how will it help humanity? For instance, how many computers will it make jobless, the quantum computers? And the second is, what is the next step?
Well, I mean, why is it good for humanity? That's a good question. Because
maybe it will save energy, no more computers. Only one quantum computer will do it all.
Well, again, I don't think that's ever going to happen because again, a quantum computer is not a magic wand that solves every problem faster. Many problems cannot be solved faster on a quantum computer. So your old-fashioned computers that are on your desk or in your phone will do perfectly fine. So it's not the case that that we will have only one computer that does everything, or sort of Lord of the Rings thing. Why is it good for humanity? That's also an interesting question. In a way, we're all scientists, and we're trying to figure out what you can do with something. And potentially, it could lead to, but again, this is just a wild guess, but it could lead to better medicines or to better superconductivity, which, as Rami actually had in his slides, will help solve part of the energy problem. But I mean, these are all big words. I mean, we just don't know, but it could potentially work towards that direction. Or this fertilization is another example of what's potentially could be done much more efficiently. And God knows what else. But I mean, I might give you back this question, and let's go back now 60 years when there was no real computer, and you are sitting now where I'm sitting, and someone is asking you, why do we need a computer? Why is it good for humanity? And then you wouldn't know the answer. But if you look now how computers are everywhere and how important they are. So we have a gut feeling that it's going to be important, and then that's going to be good for something, and we have some clear indication that it actually is.
Yeah, but we have to be honest that it's an enabling technology. It is not the computer itself is not the purpose of mankind. We hope it helps in other challenges like energy problems, whatever. But it's not up to the quantum computing community to focus on this.
Let's talk for a minute about
and one of the examples is, for example, is in some examples you might not even know it. I mean, one of the hopes is that we could use it to train classifiers. For example, if you search for a cat or dog and select images, you should get a picture of cats and dogs, and that's a classical computer which is trained to recognize such systems. And such classifiers could be trained using or with help of a quantum computer. So the only thing you'd notice is that your searches would come out better. And
cool.
yeah, in fact, you don't directly interact with the quantum computer, but it does enhance your experience.
But is that the business case for Google?
Yeah. That is one of them. The other one is, as I showed, is perhaps we can help develop. I mean, far future, maybe we can help develop a reaction catalyst or help materials research.
But one other example where you say, when you talk about picture recognition, I mean, you just, if you've ever been in a hospital and you had to do an X-ray, 3 people standing around your X-ray and all of them have a different opinion. So it might be a possibility of using this picture recognition also for something like, is there really some breast cancer cell in that picture, yes or no, where you could have some educated guess on support by a computer, which goes beyond figuring out whether there's a cat on a picture or not.
No, so very useful.
But that's around already, actually.
Yeah. You know, and there's a question about the haves and have-nots here, and the question, I suppose, is really cemented from the idea that initially there was some concern, especially after the release of the Snowden documents, that the NSA had for some time been working on a quantum computer, and then I think that actually in the documents it was revealed that it was like only a few qubits that they wanted to achieve by X amount of time. But it brings up the question, how much of this research can actually potentially be done when a lot of the figures in the academic community are known globally and known to each other? Is there a possibility of such a computer being developed in secret?
No.
No, hey.
No, of course. I mean, of course, it could be done in secret, right? If you have a big team of people and you don't tell anyone that you're working on this, it could be done. I mean,
it's interesting because it depends on who you ask, because there are other people who say that it absolutely cannot be done in secret because you need the support and the intellectual resources of the academic community that's currently working in this field. So that means you would be known, at least to this community.
Difficult question. I mean, at the moment, we need the whole academic environment to exchange ideas and come to new strategies and develop the platforms that will eventually lead to a quantum computer. But you see that some platforms are getting more or less defined and how they might look like. And then most of the scaling and engineering tasks is also what we do in Delft a lot. We bring together quite a lot of different engineering disciplines to make the speed up of the development. Well, that's the kind of development or R&D that you can also do in a closed environment.
Yeah.
I don't say that's the preferred option, but it is possible. Yeah.
But Grégoire and I were together at the European Commission when we saw the research and the amount of money. So the Chinese have every year a 5-year plan, and we saw that they had devoted significant financial contributions to this field. However, it was in direct disproportion to the amount of research papers and public information regarding the research that was actually conducted. So they put a lot of money in, but they don't publish.
Or they're trying to catch up with state-of-the-art knowledge.
I love these discussions.
So I try to make it more positive.
But maybe a difference there is also that you ask whether they could do it secretly. On the other hand, the academic environment just works and strives on making everything that we do public.
Exactly.
So I can look up all ideas besides the most recent one from Harry by just looking at the papers. I don't have to talk to Harry. I can just read on his ideas, approaches, algorithms. Everything is there for grabs. There is no IP in that sense. So
no, but it's conditional on publishing.
But he does because he's bound to publish.
No, he does.
Yeah.
But the question
you could imagine an asymmetric situation.
Well, NSA doesn't.
No.
They can just take all these ideas and implement it. There's nothing stopping them from doing that.
No, exactly. So they could be indeed catching up.
I don't see why they shouldn't be able to do that.
So your answer is yes.
No, I'm not saying that they do. I say in principle, because everything is published, it's possible.
Yeah. Yes, exactly. We have a question.
Yeah. How can we trust the outcome? Because we are putting something in a black box, and we want to answer for it. For Google, we say what is 1 + 1, and Google can say 3 or 5 or 6. And that's my question.
I'm going to let Google or Rami answer that.
1 + 1 is 3. Yeah, that would be a pretty big problem. No, that's a good question. So, for example, with this quantum supremacy experiment up to 4042, you could check with a classical computer, and beyond that, you can't really do that. Yeah, you can basically check all the way, and then above that, you'd have to trust whether the next, adding the next qubit is still right. But I would say that quite a few examples in the applications I showed is materials research and chemistry. And you could use nature as your baseline. Sure, if a quantum computer would suggest to make a certain reaction catalyst, you could go ahead and make it and see whether that works. And if that doesn't work, something was messed up. So nature in that sense is quite a good check for these things.
It's also,
but it depends, of course, on the application.
But it is also how the pharmacy industry. Some people at least say that the quantum computing eventually might help. It might help to speed up the trial and error phase. But in the end, your experiment is still in the clinical testing phase.
I might add something to what Rami said. And I think your question is a fantastic question. It's a beautiful problem of how to verify a quantum computation. And actually, there have been some nice proposals from actually the classical computer scientist community. They're called interactive proof systems. And the idea is that instead of running your quantum computer once, you run it several times and you start into a dialogue with it. And it's very much something like the following, and this is sort of not what a quantum computer does, but as an example, suppose that I claim that I can tell very well Pepsi Cola from Coca-Cola. But I mean, you have no idea whether I can do that or how I do that. But nevertheless, I can convince you that I can do that by the following test. You prepare, without telling me, a glass of Coca-Cola or Pepsi Cola, and you give it to me. And I taste it, and I tell you, this was Coca-Cola. And we do this 100 times, and you randomly give me one or the other. And I have it 100 of the times I'm right. Well, that convinces you that I am able to tell Pepsi Cola from Coca-Cola without you knowing how I did it. And in a very much the same vein, you can actually interrogate your quantum computer to know that it actually computed exactly what it was supposed to compute. Although we need a lot of qubits, Rami, many more than 9 or 22. But in principle, there is a modest overhead, like error correction, that you can add to your computer, and you can be absolutely certain that at least it computed what the program said it had to compute.
And maybe if I can add something along these lines also, we saw the random number generator, the quantum random number generator. You know, if you get random numbers from a device, it's impossible to tell if they are really random or not. And the device actually, Harry doesn't know it, but there's actually a memory, and it just reads always the same numbers. And so Harry, and you cannot. Yeah, you've noticed.
Yeah, it's just very old. So
you've had the device for a long time.
Yeah.
But basically, you cannot check. So the way to do it, if you want to verify that you have a good random number generator, is you can look at the statistical properties of the numbers, but again, they could be nice numbers which are in the memory, so you need to open the box and look at it and look at the source code and everything. And so that's it can be a difficult task. And quantum technologies can give you an advantage here because there's another approach to generate random numbers. It's something that physicists call device-independent random number generator, and the idea is that it's a quantum device where you can test you as a user without knowing what's in the box. You can do some tests and then get an estimate of how much randomness you can get out of the box, and that's something that is completely infeasible using classical technologies. So now that I have said that, I must say that it's not practical yet. There's still a bit of work before such a device can be made small enough, commercial, etc. But I think that's a very important and nice application also of quantum technologies along the same lines.
Yeah, and not trusting your device.
Exactly.
But analyzing the data by classical means.
Yeah. So Harry just asked Rami for more qubits.
Yes.
Yeah? And the thing is that there's this company, you saw that in the previous slides, called D-Wave, which says to have 1,000 qubits. But I suppose the question is, are all... 2,000.
Yeah,
2,000
qubits.
qubits.
2,000.
But what we didn't talk about is, are all qubits then created equal? What's the difference between a quantum annealer, which was also mentioned in one of the slides, I think, versus a universal supercomputer, and what's in between? Want to go take that?
This is sort of a...
Rami?
Yeah, sure. So a quantum annealer is a special purpose device which excels at, for example, finding minimi potential landscapes. And you can map quite a few problems on that, in that physical form. And for that, you, in principle, don't need to have a lot of coherence. You do need a lot of connectivity because you need a lot of spins or quantum mechanical spins to tunnel to find those local minima. That's different from a full error-corrected quantum computer in the fact that an error-corrected quantum computer can, in principle, run any algorithm in a manner that is protected. And for example, what we did is we actually simulated an annealer using a digital quantum system, a quantum device. So large chemistry simulations, any kind of large problems require lots of qubits. Mm-hmm. And when you have more qubits, you have also more sources of error. And then at some point, error correction becomes a necessity. Mm-hmm. And a quantum annealer in principle, doesn't have full error correction.
So to kind of summarize, universal quantum computers are cooler than annealers.
Literally, I guess.
Well,
I wouldn't put it like
well.
that.
Colder.
I mean, the error correction allows it to be used for more generally sized problems.
Yeah.
Yep. We have one more question.
Are you in fact saying that because many computing problems are in fact search questions where you have heuristics trying to find the optimums? I think simulated annealing is one of those. Does it mean that you can have an earlier a solution for search problems so that you may circumvent, or maybe that it doesn't really matter that you have some errors because you're finding optimums, and you can simply check if the solution that you found is better than the ones you found before? So that you have, like the decryption problem, that you can validate the result yourself and that you can search large spaces in a quicker manner, even if you don't have the error correction completely in place. Is that the case?
No, that's not the case. Well, first of all, you can have... It depends on the problem whether you can use a search algorithm or not. Most problems actually, you cannot speed up even with quantum search. That's one. Two, actually, in order to perform the search algorithm, you need error correction. And if you don't have the error correction, you actually get random noise out of your computer. So it's not the case that because it's faster, you don't need error correction. You do need the error correction. And then in certain cases, you are more efficient.
Thank you.
So you always need error correction.
I have a question over here. Yep.
I have a question about after 10 years ago or something. Suppose we will get a quantum computer working properly. As a developer, do I need to learn some new paradigm, or we can use current programming language to program the software on the quantum computer?
So I guess that's one for me. You really need to program completely different a quantum computer. I mean, and actually the quantum computer will, of course, interface with your classical computer. So part of it will be just the classical part that drives the quantum computer, or that uses the answers from the quantum computer. But the purely quantum part is not like a normal quantum programming language. It's really different. It has to use this both superposition and interference in a cool way so that it does something useful for you. And that is not something that you have on a classical computer, and also not on a classical programming language. So you need to learn to program quantum computers, and that's why I also, on my wish list, was training of new people who know how to do that.
On many different levels. I mean, on the machine language, the control, the error correction,
also.
the application.
Hold on 1 second. Please wait for the microphone. It's right behind you.
Yeah, I would suggest that the compiler would be made available or developed, and then you can use, I guess, your classical way of programming to use it. Or is it?
No. Again, if you want to address if you want to tap into the power of superposition and interference, or into the quantum power, you really have to program differently. You really need to use different ideas.
Yeah, okay, but I think maybe that is solved then by developing a good compiler. So that is doing the difficult job for you.
I hear a challenge and like a potential.
No, the compiler will help you. I mean, you will need a quantum programming language, and we actually have one which is with gates, with Hadamard gates and CNOTs and rotations. And then what your compiler will do is translate that into what the qubits actually do. But the thinking has to be different from the thinking that we have now. And a compiler is not going to solve that.
Jaya, may I ask a question to
yes,
the other
course.
panelists?
Yes.
Oh, yeah.
to the audience.
And the audience.
And then we're going to take the next question over here, okay? So there was one more question over there. We'll take... Can we just do... I'm really happy because the audience is warming up.
It's related to the current question. You know,
okay,
if you look at the technology startup scene, there starts to be some companies that claim that they do software for quantum computers. One is called 1QBit, I guess. There's one called QCware. Do you guys know what they do? Is it really something where, is there some substance behind what they do? Or is it writing program for D-Wave? Any idea of what this is all about? Because it's a bit fuzzy.
I haven't talked to them, but I think one part would be to get patents. I mean, that would be one way of being a company, I think, to obtain patents of new quantum ideas. But what the
algorithm,
you mean? Or
yeah, I mean, it could be that, and not that I'm doing that, but it could be that I have a wonderful idea of an algorithm, and that I first patent it, and then tell the world. But I have no idea what these companies are doing. But maybe you guys.
I don't know much more than you do, and it's quite disconnected from the activities we're working on at the moment. Where you have first you find your software layer. It really depends on the actual implementation of the qubit, and the layer on top of it is dealing with the gates, more or less independent of the physical implementation, and then the compiler level and the error correction schemes. And hopefully, in the end, we can make that physical qubit independent and standardized, that you don't have to learn 25 different compilers and languages. But a long way to go. So it's a good question, and there's a lot of work to do in that area.
Who has the microphone? I guess you're up.
Well, actually, my question is something in between the compiler and the physical implementation of qubits. I'm from the classical computer science. So you have the von Neumann cyclus and the ALU, which actually computes the computation. How do you put in the instruction into a certain? What is actually the architecture of a quantum computer?
Yeah, it's a tough question. I mean, we're studying this. I mean, we don't know yet. I mean, likely it will not be a von Neumann-like architecture. So a different architecture, meaning that we have to rethink quite a few assumptions from the classical computing architecture.
If I may be of help, in a von Neumann system, there is a separate memory, a bus, a CPU, a disk drive. These functions are separated. And that is maybe not the right way to think about when it comes to a quantum computer. In a quantum computer, you essentially have your physical qubits, which are protected with error correction. And on top of that is a logical layer where you perform algorithms and store data at the same time. Now, storing data is kind of not very useful if you don't use it, because it is quite expensive to store data and correct that. So it's more that data and algorithm are intertwined, and at the end, Remember, at the end, you pull out one classical answer because that's what measurement does to quantum states. So the von Neumann architecture is not really quite the right way to think about quantum computing.
Yeah. We had one more question back here, of course.
Yes, so talking about architecture, I just saw Rami's like a chip, maybe like a quantum device. How do you hook up like two quantum devices? Do you use like a fiber connection, or because if you make one quantum device and then you want to use the second one, you're not going to make like one big chip. You're going to hook them up, I guess, right? And how does it work? It's a question to Rami. Yeah.
Yeah, this is a very good question. Now, I mean, these wafers can be 4-inch or 6-inch, or I think even now 8-inch, and the qubits are, I think, 200 by 200, 300 by 300 microns. So we can put more than 9 qubits on a single chip. But eventually we'll need to implement chip-to-chip communication. And whether we'll do that optically or with microwave, that's something we haven't figured out yet. But it is something which will be necessary eventually.
Okay, thanks.
This challenge is part of the trade-off between the qubit devices. I mean, the superconducting qubits seem to be very advanced and pretty popular at the moment, but they're massive compared to the transistor on your mobile phone chip. So in the end, you cannot squeeze too many of them on a single wafer. A spin qubit, for example, many more would fit on a single wafer. So you can maybe have tens of thousands of qubits on the single wafer.
And you still would have to bring in the wiring, and that is one of the challenges.
Connectivity, connectivity is a major challenge here because we don't have the word and the bit lines like in a classical chip. At the moment, we have single lines towards every qubit, and often multiple lines per qubit. So the number of lines is incredible, and it all has to go down to this 20 millikelvin. So you understand that doesn't scale that way. So we have to do multiplexing, other things. And the NV centers in diamond or other optically addressable qubits are interesting for that point of view because they may give other options to read and write or interact with the qubits. So it's a big puzzle, difficult trade-off. Yeah.
I'm going to take one more question. There's 2 here. You've already asked 2. I'm going to be fair. So you had a question. Can we get the microphone over?
Thank you. Sorry. Maybe a funny question. Will Moore's law still be applicable to quantum computing?
Not in that sense, but we still need Moore's law because we didn't discuss about it. But a quantum computer at the moment needs a huge amount of classical electronics to control the quantum computer. So we are happy with Moore's law giving us more powerful classical electronics to control our quantum computer.
And I actually hope it is applicable because it means that every 2 years or so, the number of qubits doubles.
Yes.
That would be great. Yeah.
So
yeah.
I think it is applicable. I hope at least.
I'm going to ask you a final question, and I can't believe that we have this. This is really, I'm very proud of you as an audience. You did very well with very tough material. But I'm going to ask a question about the future, actually. And what do you see as the most important quantum developments for the next generation in terms of how they change our way of life? We talked about, the fertilizer issues, but can it actually help with simulations that we would run, for example, for the human genome or, database searches or interstellar travel, stock market queries? Where are we going to? And you also talked about the different disciplines and skill sets we need in order to do this. So it's physics, mathematics, computer science, all converging. What are the other skill sets or the multidisciplinary approaches that we need, since the theme of Alert Online is skills, and this is a beginning area for us? So what do we need, and how are we going to get there, and what should we be working on?
So from what I see in the lab, I guess it's the same for most experimentalists. There are theorists that have really good ideas, and they sometimes get ideas from yet another field. Let's say there's a really good chemistry idea, and quantum theorist picks it up, and then he translates it to the experimental physics part. And so it just needs more interconnectivity to make the chemistry community talk to the quantum people, to first give the bio and chemistry and medicine people a good reason to talk to the physicists, if you want, or the engineers, or whatever you want to call them in the long run. Give them something where they see a reason to talk to us, and then we have some new playgrounds that we might not have considered because we just don't talk to a biologist about some problems that we haven't considered yet. A chemist, someone from medicine about new drugs. There is probably something floating around, but we only get to learn about it when we bring people together, maybe at another panel discussion, and say, yeah, there is something, but it only works when we bring the right people together.
Well, you mentioned quite a number of potential applications, and I think this field is so new that D-killer application is probably something we didn't foresee as of yet.
Yeah.
So act surprised, and when it comes so far, when it comes to skills, I mean, you're pointing in the right direction. I mean, what we have now in the lab is having people from material science and physics and machine learning and microwave technologies and analog electronics in the lab working together with the quantum scientists, and that's a huge investment, but that is what is needed. I mean, in the end, we also have to, on the industry side, we need the people that have their background in playing around and thinking and breathing quantum, but working on the scalability. I mean, and that investment, I think, is important per country or per area where we want to focus, set up this kind of hubs or communities to work on. And I think that generation will eventually bring us the quantum computer.
And it's a cascade effect, because we heard that theorists must talk to experimentalists and other scientists. Then experimentalists must talk to engineers in an academic setup. My challenge is to take something that is demonstrated in a university environment and to make a device out of it. And so I need more kind of industrialization engineers, and they must be curious enough. You cannot find them with the quantum skills that you need, but you need to choose the people that are curious enough so that they ask the question, just like what you did. They don't think they don't understand it, but it's not important. They actually ask the questions to the physicists so that they can make the right choices and the right design. And so that's this state of mind that is very important.
And I'm going to ask you, Rami.
Yes. So, so I think there are two types of use for a large-scale quantum computer. One is that it is being used by, for example, companies like Google, where classifiers are trained in such that your search or your experience on the internet improves, and in this way, you don't really notice it. But a quantum computer could then be responsible for improving, the internet experience of billions of users, and that would be really great from our point of view. The other way where it could be used is, for example, for cloud access for research institutes. And I think a good way to think about it is that back in the 1950s and 1960s, large mainframes were installed in a few universities, and people could make use of that. People could make use of that. Well, now we have the internet, so I think cloud access for a few quantum computers, which are then accessed by research institutes, perform chemistry simulations, physics simulations, materials development. Now, when it comes to the skill set, quantum computer or developing a quantum computer is at a very interesting crossroads of quite a large number of disciplines. I think the panel members already discussed that. You need to know the physics of your platform, and in my case, that condensed matter physics. I need to know what a superconductor does. It is algorithms. It is electronics, software. You need to be able to program the firmware of those boards, but also at a higher level the algorithms. And you also need to understand quantum physics. And it is very interdisciplinary, and it actually, joining Google has helped me because I got exposed more to software. So you really need to pull up on quite a few number of disciplines, and this is why it's also so important to keep an open mind and an open approach to people. And I guess I'm lucky that I'm here with Google, because I also see that there is a Silicon Valley approach to trying to build a quantum computer. Silicon Valley means that there is openness, people are open to new ideas. There's also an open tradition of open discussion. There are focused initiatives, there are career opportunities. There's also funding available. And I think that combination of openness, of interdisciplinary, to basically construct a quantum computer is a giant, difficult task ahead, but challenging, is something that is, I think, sorely needed. And I would say that is something that has changed in recent years. I mean, superconducting qubits got started in, I think, 1999. I think that was the first time that people actually did coherent manipulations. And it's 2016 now, and it's only a few years that these large efforts started. So I think these are exciting times, but at the same time, it's important to keep an open mind and to engage the academic community. There's a lot of smart people, a lot of great ideas out there, and I think a combination of them will make a project of building a quantum computer successful. And I think any kind of not engaging other people is not healthy for advancement.
Yeah. Harry, your final remarks?
Yeah. So I don't have if I had a killer application and I hadn't told you so, then that would be a bit strange,
You're
right?
Saving it for patents.
Yeah, no, not for patents, but I would have told you already in the beginning, so that I don't have anything to add to that. All I have to say is that it's just very exciting, and we have no clue really beyond what we've seen what lies ahead of us, but that's just the challenging and interesting part. And concerning the skill sets, I do think we need people on all these areas that sort of learn a little bit from everything and then can work together and can talk together. Actually, common language is also something that is not an automatic given thing. It takes time to understand each other and to learn each other's language. Yeah. So, but when you get that from the start, it already gives you a head start. So I think we need to have young, bright kids that solve all our problems.
Always good. I just want to take a moment to kind of encapsulate everything that we saw today. We started with a picture of the moon landing. My family lives in Florida, my parents actually. And so every once in a while I get a chance to go to Cape Canaveral, Kennedy Space Center, and take a look at the actual computers that did the first moon mission. And seriously, I wouldn't be an astronaut and trust those computers and go to the moon. No. So if you think about where we are and what this field could potentially mean to our future, I would encourage, if even one person gets inspired to help these pioneers or think differently, or like you said, young people, infect your children with things that are going to be part of our common quantum future, I urge you to do so. And I want to thank you all for taking the time today to come to this panel, because it's not the easiest thing of the 3 choices you had for Alert Online, and really help get us better with those cybersecurity skills, and maybe even start here. Thank you so much. Thank you. Thanks, Rami. Thank you to also all of our panelists. Can we give them one more round of applause? Thanks. We have some refreshments over outside, so after such a long sitting, you probably would like to have a cup of coffee or tea or some wine, and there's some little warm things that'll come by, so please take this opportunity. And they're still around for a while. Yeah. Yep. Okay. Thank you.
Stay the whole month.